Okay, so in the world of serious, high-stakes computing, there's this idea, this assumption really, that you have to choose. You can either have results that are perfectly reproducible every single time, or you can have results that are fast. But you can't have both. Well, today we're going to tear that idea apart. We're going to see how a system that's built for absolute mathematical perfection can, believe it or not, actually run faster than one that's just built for speed. Let's get into it.
So let's just start with a fundamental, kind of mind-bending question. Imagine two computers. They're identical, right down to the model number. They're running the exact same code, with the exact same input data. Should they produce the exact same answer? You'd think so, right? But the answer is a resounding yes, they can, and often do, produce different results. And this isn't some weird theoretical puzzle. It's a huge, dangerous problem in the real world of distributed computing.
There's actually a name for this phenomenon, and it's a great one: spectral divergence. You can think of it like a ghost in the machine, for real. It's what happens when these tiny, almost immeasurable differences in how the hardware itself handles numbers start to add up. They cascade through the system, getting bigger and bigger, until two machines that are supposed to be in perfect sync are suddenly living in completely different realities.
So to find this ghost, we have to go look at the very foundation of how most computers do math with any number that has a decimal point. And the culprit, the source of this ghost, is something called floating point arithmetic. It's the standard, it's everywhere, and it has a tiny, almost invisible flaw baked right in.
The whole problem really boils down to something called the rounding boundary. So look at these two numbers. They are incredibly close to each other, right? They only differ way out at the 12th decimal place. To you and me, they are basically the same number. But to a computer chip, one of them might be just a hair over an invisible line, which tells it to round up, while the other is just a hair under, telling it to round down. And right there, that's where the ambiguity, the uncertainty, creeps in. And here's what that looks like in the real world. Let's say your system is running on a bunch of servers. Maybe some are on Google Cloud, some are on AWS. You feed the exact same number into a CPU on GCP and another one on AWS. Because of these teeny tiny differences in their physical hardware, one chip rounds up and the other one rounds down. And just like that, you have two different results from the exact same starting point. And that tiny little disagreement, it does not stay tiny. It leads to something the source material calls a zeroth order rupture. I mean, what a term. It's basically a fancy way of saying a total, catastrophic system failure. It's a complete structural breakdown, and it all starts from that one single, impossibly small rounding error we just saw.
You see, it's this cascade effect that's so dangerous. It all starts with one tiny flaw. A single number is rounded just a little bit differently on one machine. But that tiny error then gets fed into the next calculation and the next, and it spreads like a virus through millions of calculations across your whole network. The different computers start to drift further and further apart until, bam, the system ruptures. Consensus is totally lost, and the whole thing just breaks down.
So, how do you solve a problem that's literally built into the silicon of our computers? Well, the OPHI architecture doesn't even try to patch it or work around it. It enforces a completely different way of doing math, one that is designed from the ground up to make this entire class of failures completely impossible.
Let's just take a really simple example. Say a sensor takes a reading, and that value is 0.6120. In pretty much any standard system today, that number would be stored as a floating point number, and it would bring along all those risks of ambiguity and error that we've been talking about.
But the OPHI solution is, well, it's just so elegant. It completely gets rid of the decimal point. It does this using a concept called a scaled integer manifold. So our value, 0.6120, gets multiplied by 10,000, and it's stored as the whole number 6120. No decimal, no ambiguity, no rounding problems. It's just gone.
And the rules here are super strict. The mandate, the law of the system, is that every single value, every sensor reading, every internal state, every variable is represented as a 64-bit integer. The whole goal is to achieve something called bit-level determinism. And the result? Every single computer in the network, no matter what CPU it has, no matter where it is, will produce the exact identical string of ones and zeros for any calculation, every single time.
Okay, so this is where we get to the heart of the matter. Achieving this level of perfect, bit-for-bit identical results, it sounds like it's got to be expensive, right? The common wisdom, the gut feeling, is that you must be giving up a ton of performance to get this kind of mathematical purity. I mean, this is basically what everyone assumes. It's the conventional wisdom. If you want determinism, you're going to have to pay a performance tax. Your system is just going to have to run slower. But is that really true? Let's just put these two approaches side by side.
You've got standard floating point math, which is non-deterministic. It's totally dependent on the specific hardware you're using. And like we've seen, it comes with a high risk of a catastrophic rupture. Then you have the scaled integer approach. It's bit identical, has zero hardware dependency, and it completely eliminates that risk.
But here is the big twist. Look at that last row. When you look at numerical and energy efficiency, the scaled integer approach is actually higher. The deterministic method is faster. The trade-off that everyone believes in, it's a total myth.
So why? How is this possible? Well, it turns out that simpler math is just faster math. By sticking to integers, the system completely avoids all the complex, power-hungry logic that's built into modern CPUs just to handle floating-point numbers. It's optimized for simple, lightning-fast operations. And it's so efficient that you can run it effectively on local hardware, without needing some massive, no-limit cloud budget.
So, what are the big picture implications here? What happens when every single calculation your system makes is like a perfect, verifiable, and efficient brick? Well, it means you can build an entirely new kind of system, a whole new class of computational structures on top of that rock-solid foundation.
This is what the OPFI execution pipeline looks like. It starts by taking a sample from the real world. Then, that signal is processed by a totally deterministic operator. Next, it gets validated against a strict set of mathematical rules to make sure everything is stable. Then, any potential ambiguity across the whole network is resolved into a single unified state. And finally, that validated state is fossilized. It's committed to a permanent, unchangeable record.
And that permanent record is called the Merkle fossil ledger. You can think of it as a history book for the system that can never, ever be changed or rewritten. Every new state is cryptographically chained to the one that came before it. This creates this perfect, tamper-proof, completely auditable timeline of the system's entire life.
And having this unlocks applications in fields where you absolutely cannot afford to be wrong. We're talking about AI systems where you need to be able to audit every decision. We're talking about safety-critical systems in airplanes and factories, high-reliability manufacturing, stabilizing national power grids. In these areas, being able to prove with mathematical certainty how a system made a decision isn't a nice-to-have. It's everything.
So, we'll leave you with this final thought. What this architecture really represents is a fundamental shift in how we think about computing. It argues that computational truth shouldn't be this fragile thing we just assume is correct, something that can be knocked over by the random whims of hardware. Instead, truth can be something we build, a verifiable artifact that's produced through a rigorous, deterministic, and, as we've seen, highly efficient pipeline. So the question is, what becomes possible when we can start building our world on that kind of foundation?